What's up guys, this is Jahangir from MedPorium, and today we're going to be talking about integrated rate laws, specifically for first order, second order, and even zero order, and we're also going to go through some practice problems. So let's talk about first order. So with first order, here's what the equation may look like. And first order is really characterized by this natural log. So anytime you see maybe on a graph, like it says natural log of the concentration, or anytime you want to find the rate constant over here, the rate constant, you're wanting to find the rate constant, you're going to have to use this natural log. Or you could have it with e to the power of negative the rate constant times time. But first order is really characterized by this natural log over here. And over here, this is concentration at a specific time. So we can say concentration at a specific time. And over here, this is concentration when t equals 0, or when time equals 0. And that's what really makes the A sub 0 our initial concentration. So A sub 0 is our initial concentration, A sub t is our concentration at a specific time. Now that's first order, and if you guys aren't giving these formulas on your formula sheet on the exam, then I definitely say that you should memorize these formulas, and especially since this sort of holds that y equals mx plus b format. So if I sort of arrange this over here, move this over here, so it could be something like this, just to show that y equals mx plus b. So this would be y equals mx plus b when you're doing that sort of graph. So that ln of a sub 0 would be your y-intercept. Over here would be your slope, and the y equals a sub t would be your y. So now let's move on to second order. In second order, this is the y equals mx plus b format that we were talking about, but this is specifically for second order. And in second order, it's going to be 1 over the concentration. And that is what characterizes a second order reaction. Now, one of the things to note about this rate constant and time, because you might be wondering, well, what units are time? Because maybe you remember that the units for Gibbs free energy, that temperature is supposed to be in Kelvin. So what units are the time supposed to be? Well, it really depends on our rate constant. Because if our rate constant, and I'll just draw an arrow over here, if our rate constant, and this is second order, it's going to be m to the negative, and I believe it's negative 1 power times seconds to the negative 1 power. Whatever that rate constant unit is, that's what your time is going to be, because they have to cancel out. So if it's seconds over here, your time is going to equal seconds. And just to sort of visualize this a little bit more, let's just throw out a random number out there for our rate constant, and let's just say our rate constant is 5.0, or just 5. And our units would be 1 over m times s. So this is our units for the rate constant, and for time, we can just say like 100 seconds, for example. 100 seconds. So those seconds have to cancel out. They have to be the same units for them to cancel out. Because we can't just, and I'll just sort of take this out right here, we can't just write time as 1 hour, because seconds and hours don't cancel out. So it really depends on what units your K is. And this matters for pretty much every chemistry math problem you do. Even with using the universal gas constant, you have to look at the units and you have to be able to cancel them. So now we know that for second order, let's look at zeroth order. So zeroth order is just plain out just concentration, and that's zeroth order. And this is the formula for zeroth order. So if you don't have this on your formula sheet, then definitely memorize this. But this is pretty simple in terms of chemistry, in terms of solving those problems, because all you have to do is just plug it in and see how it goes. Alright, so let's go through this practice problem right here. And it's telling us the reaction constant for the decomposition of N2O5 is, and I'll just highlight that, negative 3 or 3.7 times 10 to the negative 5 seconds to the negative 1 power. And automatically we can tell this is first order, because seconds to the negative 1 power is the K units for first order. And if you haven't seen the previous video, I talked about reaction rate, constant, and order, and I actually made a graph showing you guys how specific K units can correlate to reaction orders. So seconds to the -1 power is specifically for the first order. And you really have to know this because sometimes some questions may not even tell you what reaction order it is. So it's really good to have that as background information. And it says, how long will it take 80% of our N2O5 to decompose? Now, automatically, it didn't tell us the initial concentration or the final concentration. It's asking us for time. And you don't have to freak out. We really don't have to know the initial concentration or the final concentration in order to find our time, because we already have this information, the 80% of the dinitrogen pentoxide to decompose. So how long will it take 80% of it to decompose? Well, on the flip side, we would be left with 20% of N2O5, because if we're getting rid of 80% of N2O5, then we're left with 20% of N2O5, if that makes sense. So we're going to be having 20% of N2O5, and that should be our concentration at a specific time. So this should be concentration at a specific time. And now that we know that, we can just plug in our numbers. So it would be ln, and we can leave this as x. So x is showing us what our concentration is, because we don't know our concentration, but we know that we're left with 20% of it after a specific time. So once we know that, we can plug in our k as well, 3.7 times 10 to the -5, t over here, so t's are seconds, and all automatically we can just get rid of the x's. And this is what I mean when you don't really need the initial concentrations, because we're just denoting it as x. It's still going to be the same, but we just have that 20% that's left over. So this turns into ln of 5, because 1 divided by 0.2 is 5. So just made it a little bit more simpler. And we're going to divide the 3.7 over. So 3.7 times 10 to the -5 equals our time. And remember, our time is in seconds. Now, I'm going to be honest, I'm a little too lazy to put my units, unless this was a free response question, an exam, which you're definitely going to have to put your units. But for this question, just going to roll with it. So it's ln of 5 over 3.7 times 10 to the -5. And that gets us 430 or 43,498.32 seconds. Now, since we do have to put this in proper sig figs, so one thing we could do is, since we were given 2 sig figs, which is our lowest number of sig figs that we're given, so that's 2. So that we could write it as 4.3, and I could do this math right here. So 1, 2, 3, 4. 4.3 times 10 to the 4 seconds. And that would be our answer for this question. So it really is as simple as plugging in and finding your answers, but I just chose this specific question because it is a little bit harder to grasp at first, since you're not given the initial concentrations, you're not given the final concentrations. So you don't have to fear that part, because we can just denote that as X and we can just go on with the same question. And more than likely, they're going to give you these percent problems. So just sort of visualize it and also try to use the wording to your advantage. So it says, how long will it take 80% of that N2O5 to decompose? The opposite of that would be, we would be left with 20% of N2O5. So it's just subtle words like that that you really need to pay attention to. But more than likely, the most common questions you're going to see, they're going to give you the initial concentration or the final concentration. They're going to ask you the time. So don't worry about that part. This is just a quick question on first order reaction rates or reaction orders. And that's pretty much how you find time, or how you use this sort of equation. So now, let's look at some graphs real quick. So let me try to zoom out over here just to get this in frame. So the question is asking us, write the reaction orders for the following graphs. So automatically we can see that we have an ln of hydrogen peroxide, and that's a straight line. We have 1 over concentration of C4H8, which is a straight line, and then we have concentration of ethanol over time. So if we remember when we were talking about first order, second order, 0th order, we said first order is characterized by this ln. So this is automatically first order. And at that ln, it's a straight line. And this is the most important thing to note. When it is a straight line and you look at the y-axis and it's ln, then that's first order. But it has to be a straight line, because if this was maybe a curved line, then that wouldn't be first order. So it has to be a straight line. Now over here, 1 over the concentration. Well, we talked about 1 over specific concentration is second order. And since that's a straight line, that is second order. And we sort of skim by 0th order, and 0th order is just concentration. And this is just plain out concentration. So this is 0th order. And that is pretty much reaction orders in terms of looking at graphs and using integrated rate laws.